Immersion is often cited as one of the defining qualities of excellent games. However, our understanding of immersion and factors that influence the degree of immersion, such as game control, game constructions including visuals and audios, and players' time, energy, and emotion as personal investment, can still be refined. Recent developments in motion tracking technologies, such as the Leap Motion, a low-cost gesture detection hardware, allow game designers to apply and study the potential of touchless motion control for more immersive spatial experiences. As part of such a study, we create an audio-only game as a platform to focus on the adequate design for auditory feedback in order to create immersive experiences that use a gesture-based user interface. We developed two game versions to assess whether replacing explicit vocal instructions for hand positions and movements with responsive audio feedback that is suggestive of interaction methods by using environmental story-related audio cues leads to measurably higher immersion. In explicit vocal instruction version, after the story part as gesture intro, player can hear gesture instruction from the narrator, while in environmental feedback version, no instruction is given. During the gesture, player can hear non-diegetic audio feedback from version 1, while diegetic audio feedback from version 2. Once correct responses are given after the correct gesture performance, the game story will progress. In order to improve the responsiveness of audio feedback for hand gesture interaction regarding immersion, we consider audio feedback not just as a result of gesture interaction, but as an interactive signal that guides the player while going through the whole process of a gesture sequence, before, during, and after the gesture. All of these stages need an explicit auditory feedback, and we illustrate the design principles, which are anticipation, attachment, and collision, applicable for designing audio cues in different stages of a gesture sequence, using the stone throw gesture as an example in our paper. We also set up a hand gesture detection framework, supportive for players to try different approaches. After hearing the gesture intro, some players might do the correct gesture and get correct response directly. However, other players may have different reactions. Our framework would guide them back to track by providing responsive audio feedback based on their current reaction. We built our real-time hand gesture detection system based on Leap Motion API. Leap Motion API enables developers get access to the raw data of both hand skeletons, which includes palm position, tip position, grab strength, pinch strength, pitch, yaw, and roll data as measures for joint rotation, palm radius, and finger recognition, etc. The high sensitivity of Leap Motion's frame-based tracking sometimes affects the stability of detection. In order to improve this, we created gesture state to be used as the movement calculation unit for building the detection loops in our system. None, detected, action, and cooldown are 4 correct states, and ready, other, and ing are 3 wrong states. When players successfully go through 4 correct states, he can be sent back to none state by the correct looping function if gesture needed repetition. Players who do different reactions will reach wrong states and hear audio cues that guide them back to track. Depending on different story contexts, some wrong states might lead the player back to non-state to start all over again, while others would just transfer him to former state to redo the gesture in the middle of the sequence. Leap Motion software can recognize 4 basic patterns as default gestures: swipe, circle, screen tap, and key tap. This limited gesture library couldn't support natural gesture design in our project, so we built our own gesture library by creating a frame-based movement calculation method and defining the story-related gesture based on the raw data. After game development, we set up a between-subject experiment to test the immersion degree of 2 game versions. 26 subjects joined our experiment, and 13 subjects were randomly assigned for testing each game versions and filling a post-test questionnaire on their feelings on the version they played. The answers of post-test questionnaire were designed in the form of 7 Likert scales, and we built up 24 questions in total to measure basic usability, basic enjoyment, and immersion of 2 game versions. Significant differences reflected in some single questions indicate that hints in environmental feedback version are more helpful. Also, it feels more real than the explicit vocal instruction version. Responses to all the 24 questions indicate that the environmental feedback version constantly rated higher in all aspects, including basic usability, basic enjoyment, and immersion measures. In particular, story immersion is actually p-significant, which is surprising for our low numbers of subjects. Overall, our study successfully proved our research hypothesis that replacing explicit vocal instruction of hand positions and movements with responsive audio feedback and story cues leads to higher immersion.